So let's start with the fourth part of the linear regression. Now linear regression, as we have understood so far, is the next step after the correlation. It is used when we want to predict the values of a variable based on the value of another value. Now we were discussing about a exercise on weather. Now let's try and understand with some more example. Let's find the values of these metrics using our test data. So print mean is mean absolute error, matrix mean absolute error, y-test and y-pred. Print mean squared error, which is again matrix mean squared error, y-test, y-pred, and print root mean squared error. So when we print, give this kinds of command, you get a result like this. You should receive a output like this, but probably slightly different. Now mean absolute error is 3.199329178 like this up to. So and then again mean squared error, then root mean squared error. Now you can see that these kinds of result you'll get when you give this command which is mentioned at the top. Then you can also see that the value of root mean squared error is 4.19, which is more than 10% of the mean value of the percentage of the all the temperature, that is 22.41. So if you go back and see, you can see that the 4.1 is a bigger figure, that is squared figure is 4.19 is, which is more than 10%. This means that our algorithm was not very accurate. So that means, and it happens. See that is why you go for iterations. That is why you after all it is a forecast. It is a prediction. So you may or may not be correct. So if it is not correct and if you are not satisfied, you have to go further on to that. We'll discuss that also. This means that our algorithm was not very accurate, but can still make reasonably good predictions, right? So let's talk about the multiple linear regression. Now multiple linear regression, as we have seen and we have discussed, that where we have more than one independent variable, and then you are going to predict what is going to be the outcome of that. So we just performed linear regression above involving two variables that we have seen in the previous example. Almost all the real world problems that you are going to encounter will have more than two variables. Two variables are very rare, but generally you will see that there are definitely more than two variables. So linear regression involving multiple variable is called multiple linear regression or multivariate linear regression. The steps to perform multiple linear regression are almost similar to that of the simple linear regression. The difference lies in the evaluation. You can use it to find out which factor has the highest impact on the predicted output and how different variables relate to each other. Now for this, we will be working with another example, which is red wine quality data set. Now this data set related to red variants of the Portuguese Vinho Verde wine. There is a wine which is produced in Portugal, and which is the example that we are going to use for this prediction. Due to privacy and logistic issues, only physico-chemical inputs, that is, and sensory outputs variables are available. That is, for example, there is no data about grape type, wine brand, wine selling price, etc., etc. So only some limited number of attributes are available. We will take into account various input features like fixed acidity, volatile acidity, citric acid, residual sugar, chlorides, free sulfur dioxide, total sulfur dioxide, density, pH value, sulfates, alcohol. So based on these features, we will predict the quality of the wine. So whatever features were available, based on that we will try and predict. So now again we have to import all those libraries which are required, like import all the required libraries: pandas, numpy, matplotlib, seaborn, sklearn, and various sub libraries of that, and then of course matplotlib inline. Now the following command line imports the data set from the file that you downloaded from. So you must have the data set wherever it is. If you have already downloaded, it's fine. If you don't, then you can go and download it, and then you can include it in your data set. That is pt.read CSV, and whatever is the path, you can write the name of the CSV data file, that is wine quality.csv. So let's explore first the data a little bit more by checking the number of rows and columns in it. So dataset.shape gives you the number of rows and columns as it is shown here, like 1599.12 comma 12 as output, which means that data sets are having 1599 rows and 12 columns. To see the statistical details of the data set, you can write another command like dataset.describe. So this will give you all the statistical details like count, mean, standard deviation, minimum percentiles, etc., etc. Now let's clean our data little bit now. So first check which are the columns that contains nan. Nan means not a number. Now if it is not a number, that means either you have to ignore it or you have to remove it from the data set or whatever. Some action has to be taken for that. So if it has nan values, then what is to be done? So data set dot is null dot any. Once the above code is executed, all the columns should give false. In case of any column you find true result, then remove all the null values from that column using below code. So you can remove that like with this command called dataset is equal to dataset dot fill na method is equal to ffill. So this is how you can see that the unwanted kind of data can be removed. Our next step is to divide the data into attributes and labels. So X variable contains all the attributes, features, and Y variable contains labels. X is equal to dataset, fixed acidity, volatility, volatile acidity, citric acid, residual sugar, chlorides, free sulfur dioxide, total sulfur dioxide, density, pH value, sulfates, alcohol value is SY, dataset quality values. So let's check with this kind of a graph that we can now draw. That is PLT figure fixed size is equal to 15,10, then PLT dot tight layout, and then Seaborn can be used here. Seaborn instance dist plot data set, and then you can see that because the quality of the wine can also be checked with this, and average value of the quality of the wine can be seen here with the help of this graph. So as we can observe that most of the time the value is either 5 or 6. That is the kind of a output that you can receive. So next we split the data into 80% of the data for training, while 20% data to test for testing using as per the code written here now. So X train, X test, Y train, Y test is equal to train test split, and then X Y test size is equal to again 0.2. 0.2 means 20% is kept for the testing, and random state is 0. Random state means the number of iterations. Now let's train our model. So regressor is equal to linear regression, regressor dot fit X train, Y train, because here you are training the data. Now as said earlier, in the case of multivariate linear regression, the regression model has to find the most optimal coefficients for all the attributes. To see what coefficients our regression model has chosen, execute the following script. So this is the script that we have to write, that is coefficient of df data frame, pd dot data frame regressor, coefficient x dot columns, and columns is equal to coefficient. Then coefficient underscore df, when you write this, you are going to get this kind of a output. That is, it should give you output something like this. And this look at this, that various features that we have discussed earlier, fixed acidity or volatile acidity, citric acid, residual sugar, chlorides, free sulfur dioxide, total sulfur dioxide, density, pH, all these things are available given with the values. This means that for a unit increase in density, there is a decrease of 31.51 units in the quality of the wine. So just focus yourself in the quality of the wine itself. So that see the density is minus 31.51, right? Now with just one increase of 1 unit, you can see that decrease in the quality, that is density, is going to be 31.51, which is quite significant. Another factor which is significant is 1.87, minus 1.87. So these are the two factors which are very much important to look at. So increase of 1.87 units in the quality of the wine, we can see that the rest of the features have very little effect because others are close to zero. It is not very big figure. So now let's do prediction on test data. So ypred is equal to regressor, predict x test, check the difference between the actual value and the predicted value. Df is equal to pd, data frame actual, then y test predicted ypred, df1 is equal to df head 25, because again we are taking only 25 records for testing. And you can see that the difference between the actual and the predicted ones, and this is how the result will be appearing. So comparison between the actual and the predicted value. So you can see that 5 and 6, whatever was mentioned earlier, most of the values are in actual. Under the actual column you will see this 5 or 6 are appearing. 7 is appearing, but there it is very less. Then now let's plot the comparison of actual and predicted values. df1 dot plot kind is equal to bar fixed size is equal to 10.8. This of course you can decide. plt dot grid, which measure line density, line width 0.5, color is equal to green. plt grid, again you are going to draw a bar chart. That is why you have taken kind as bar. So when you write plt.show, you will be getting a bar graph like this, as we have seen in the earlier case also. So bar graph showing the difference between the actual and the predicted values. Now as we can observe here that our model has returned pretty good prediction results. And the final step is to evaluate the performance of the algorithm. We'll do this by finding the values of MAE, MSE and RMSE. Right? So execute the following scripts like print mean absolute error, matrix mean absolute error, y test ypred, print mean squared error, that is matrix mean squared error, y test ypred, print root mean squared error, and np square root matrix dot mean squared error, y test ypred, and the output will be something like this. So mean absolute error is 0.5, 0.46 something, then mean squared error is 0.384471, root mean squared error is 0.620057. So you can see that the value of root mean squared error is 0.62, which is slightly greater than 10%. As against earlier it was very high, but now it has come down and it is slightly high only, of the mean value, which is 5.63. This means that our algorithm was not still very accurate, but can still make reasonably good predictions. Then there are many factors that may have contributed to this inaccuracy. For example, you need more data. Now when you get these kind of results, it starts guiding you, helping you, that now you need more data. We need to have huge amount of data to get the best possible prediction. Maybe you may have some bad assumptions. We made the assumption that this data has a linear relationship, but that might not be the case. Visualizing the data may help you determine that. That is why visualization is very important. Poor features, the features we used may not have had a very high enough correlation also. That is also a possibility. So that means you have to go back, revise your assumptions, your whatever factors that you have taken into account. Now you can draw your conclusions that is, we studied the most fundamental machine learning algorithm, that is linear regression. We implemented both simple linear regression and multiple linear regression with the help of the sklearn machine learning library. And conclusion is that described the linear regression model, stated the regression modeling steps, explained least squares and computed regression coefficients, described residual analysis, predicted the response variable. This completes our linear regression. Thank you.